artificial intelligence. It's a big range of things, and so something that's only slightly smart might not be as complicated as you think, and we can add smart behavior quite simply sometimes, and then we can make it more and more intelligent, and then it becomes maybe machine learning, and it's kind of an automatic smartness, and then we can add massive data and mine that data for patterns and so on, and it can become kind of AI, and there's a big spectrum. So you have to start somewhere. So we're going to start with the simplest way of making a system so-called smart, and then we'll look at some of the sort of more advanced ideas, and I'll take you through it. So we'll be starting at really sort of quite simple ideas that are the basics you need to understand, and then we'll have a quick look towards the end at some of these higher, much more complex and much more powerful ideas that maybe not every application needs these even, but sometimes when you do need them, they can deliver amazing results. So let's start with some basic ideas first. So every coursework you've done in the group, as far as I'm aware at the moment, I haven't read all the reports yet, but as far as I'm aware, every single one of you has done a fixed logic coursework. What that means is your program, every time it runs, it does the same thing. It has some kind of if this, do that. If this, do that. When this is bigger than that, do that kind of logic, right? And that is good for simple systems where, if the temperature goes up, turn that on. If the temperature goes down, turn that off. If this happens, turn that LED on. Things like that, okay? It works fine, but it isn't useful for more complicated scenarios. There's a lot of systems now which are far more sophisticated and don't use that kind of logic anymore. Certainly not as a core theme anyway. Okay, so going along with that, you tend to base your decisions on what we call instantaneous state. So you're just looking at the value now. So you're looking at, for example, if the temperature is greater than 25, do something. You're looking at the temperature right now. It's like, now the temperature is 25, do something. It's not looking at the average temperature, or is the temperature going up anyway? Why? Don't turn on the heater if the temperature, if it's 25 and it's going up. That's different to if it's 25 and it's going down. Because if you want to warm the room up and the temperature is 25, but the temperature is already going up on its own, then don't do anything. So you need to look at just, the instantaneous state on its own is not enough. It's kind of too simple. So these two things, these work in many systems around the world in many different applications, based on fixed logic and instantaneous state. Works fine, but it's limited in the cleverness or the richness of the behavior. A dynamic system can be something that tries to track the external environment in some way. So we have various words that have slightly different meanings, but they're very similar. So things like, we have adaptive systems and self-configuring systems, and these systems try to adjust their own level. So, for example, maybe there's a threshold by which you turn the heating on and off, and you set that to be 25. But perhaps if the user keeps changing it, every time it goes above 25, the user turns the heating off because it's too hot. Maybe the system will learn that although the program says 25, maybe really change it to 23, because every time it goes 25, the user turns the heating off. So it's never, obviously they don't really want it to be 25. Maybe it's just the configuration is wrong. If you can learn that every time the heating gets to 25, the user turns it off, then you might adjust the turning on point lower and turning off point lower. So it's automatic, it adapts. Okay. And some of these things, you don't need to have a lot of so-called intelligence You just need to look for a pattern in behavior. So the simplest level of intelligence these days tend to be called smart systems. So these are systems that are intelligent in the way maybe an insect is intelligent, not intelligent in the way a human is intelligent, right? So insects are smart. They don't just run around randomly. They know where to find food. They know how to avoid. Think how clever a spider is, but it's not clever like a human. It's more a reactive system, but it doesn't just look at instantaneous values. It understands its context. So something like that. If you imagine that kind of intelligence into software, it's not deep thinking type intelligence. It's just having more information available and making a decision based on more than just the instant facts, right? So normally, in order to make something smart, you need some simple algorithms, not necessarily complicated algorithms at all. Sometimes just literally taking an average is enough. But you also need to understand history as well as the current state of the system. So you can't just, you're not just saying, okay, it's above 25, do this, it's below 25, do that. It's much more about trends and averages and maybe other things that maybe the user has had some inputs. Every time something happens, the user does this. Okay, then we'll adjust the settings slightly. Here's some simple examples. If you remember the very simple, if we go back a couple of slides, that is the very simple example we're trying to avoid, because this is not really a very clever system. Okay, this is a very limited behavior. Something like this is instantly clever. You can see this is much better than the previous one, because the temperature may not always, these sensors aren't perfect. And if you're measuring temperature in a room, well, the temperature you measure is largely dependent on where you put the temperature measurement as well. Where do you put this thing? Is it by the door? Is it by the window? Is it in the middle? So even your measurement is not necessarily meaningful perfectly meaningful. So, and it may take a long time for a room to warm up, and all kinds of factors. So just keeping that one example, because every other application, there are similar examples like this, right? Then if we say, for example, if we average over 5 samples and say that's over 25, you can see immediately we've got a smarter system. It's not very clever, but it's much better than the previous one with a very simple change. Now we have a much better system already. And then we can say some more things, even more clever. We can actually keep a track of the trend of temperature. It's very simple maths. If each time you measure the temperature, you put it into an algorithm and you're looking at, is it gradually going up, gradually going down? Is it rapidly going up, rapidly going down? And you can have this thing called trend. And trend could be, you could have some categories. Trend could be flat, so it's not changing, or it could be rising, or it could be rising fast, or it could be falling, or it could be falling fast, or something like this. And you could then start having much more clever formulas, such as if temperature is greater than 25 and the trend is rising, then turn on the air conditioning. And you can make much more clever decisions. But again, the maths required here is not complex, but the system would be much cleverer in its behavior. But it's not needing a lot of intelligence or a lot of data or a lot of math to do this. Okay, so these are just simple ideas so far. We need some more definitions next. Okay, so just let me have a quick sip of drink. Okay, so we also need to define discrete and continuous, because this is really important when you design something. The way you think about the way the system works in terms of these two types will determine partly how it interacts with its environment, and also partly how you can possibly make it more, so we say, smart or not. Okay, so a discrete system is something that works at particular steps. So this is time step 1. At time step 1, the temperature is 25 and the heating is off. And then you wait maybe a minute. This is time step 2. times at 2, the system, the temperature is 25.7 and the heating is on, or something like this. This would be a discrete system, and you only really measure things and do things at those time steps. So you say, okay, now we're here, and then now we're here, and then you go along another minute, now we're here, and each step you make a separate decision, and everything is separate, and you are not in between those steps. The system doesn't change. So if the heating is on and the next step is in 1 minute, the heating will stay on for that 1 minute, and then you make a new decision. Okay, and then you make a new decision, and each minute is a separate event. Now, in the real world, things are continuous, right? So the temperature in the room you're in right now is changing all the time. It's not changing every 1 minute. Okay, now it's 25.5, now it's 27. It's changing all the time. And if you're flying a plane, the air pressure on the wings and the position of the plane, everything is changing all the time. And if you're driving a car, maybe electric car with steering is done, everything is done by electrical control and not direct linkages, then again, everything is dynamic. There's no like, oh, well, every 1 minute we'll check what speed the car's going, or something like this. And almost everything you will build in your engineering life, almost everything will, the environment it works in will be continuous, almost everything. Some systems can still be discrete and work fine in a continuous environment. Okay, so for example, if you're measuring the temperature in a greenhouse or a house and you want to control the heating, you can make a discrete system work fine. It only needs to measure the temperature every 1 minute. The temperature is itself changing all the time, but you only need to measure it every 1 minute. Right? That's fine. So a discrete system that you build can work in a continuous system environment, a continuous environment. But in some environments, especially now, because obviously this course is about real-time systems, when you have a real-time system and and things are changing all the time, and some of those things are urgent, you absolutely cannot wait 1 minute before you check something again. You must be responding immediately. This is why event interrupts are so important in that regard, because interrupts allow us to react at the time they happen. Whereas if we're using something like polling or a timer to give us a 1 second check or even 1 minute, then it's not continuous in the sense that something can change, but we won't notice that change until the next sample. I just need to make a quick note of something. Just let me make a note I'd like to mention later. Right, sorry about that. That's just something I want to mention later in the lecture that I would have forgotten otherwise. So, yeah, so if we have a system that is continuous in the environment, a lot of the time we should be thinking in our design about how our system can equally be continuous, i.e., it will be looking at the system all the time, or at least any important changes will be notified to our system. So we can have a discrete system that works like the main functions work in a discrete way, but then we use interrupts to deal with anything that changes in between those steps. That's a kind of hybrid that would work. That's a nice way to enable that to work. All right, so you can have, the system doesn't have to, not every function needs to work in a continuous way, but maybe some critical functions need to work in a continuous way. Okay, so as I said before, the analog to digital conversion can run in, for example, free running mode, where you're continuously sampling something, and so it's still actually, if you're doing that, it's still discrete, but the steps are so small that it appears to be continuous. But actually, you're doing it in very small steps. So it breaks down the gaps in between the steps to be so small that they might as well be continuous. Okay. Yeah. So again, I think I've mentioned the concept of this when I say basically if you use polling or use a timer with 1 second interval, you're looking at some switches or something, see someone's pushed something. Well, you'll only notice that at the next interval. You won't, if they push the switch, you won't notice it straight away. You'll be waiting until the next interval. Think about, for example, the reaction timer I showed you in the lecture about 3 weeks ago, something like that. Now, if the reaction timer obviously has to respond immediately to the situation, there's absolutely no way could you do that with polling. It just would, the whole point would be lost because you're adding delays in, and you're taking away the randomness and making it predictable because you only detect it when your timer expires. Say, okay, see if they've pushed the button. Well, even if your timer was running at 10 millisecond intervals, you'd only be able to measure the reaction time to the nearest 10 milliseconds. So you've lost the reality, the sort of asynchronous nature of it. Okay. Now, the other thing we need to talk about as a basic idea before we can go into some of the techniques is context. And context is that, well, when your system, suppose you take your system, which if we go back to the simple one with temperature measurement, we could take the same temperature measurement code. So, okay, if the temperature is this, do that. And we could change the threshold value. And it could be if it's 25, do this or that. But it could be if it's 200, do this or that. It could be part of some industrial system where they're heating up metal or something, or chemicals or something. So it doesn't matter if it's turning something on and off at 25 degrees or turning something off at 200 degrees. It's still the same logic. You could say the same code, right? And you say, okay, this thing for my home heating, that can also be used in a factory to control a big furnace. Just modify the logic a little bit, maybe, connect it to some different sensors, and there we go. The problem is, without context, you don't know what the system is doing and you don't know what things mean. So take this statement here. The temperature is 101 degrees Celsius, right? Now, this is a statement, and this could be part of your code. You could say if temperature greater than 101 or something like that could be in the code, right? Something similar to this. And do something. So if temperature greater than 101, do something. And the question is, what is the context of that? What does 101 mean? Okay, so if the system is a fridge, if we're talking about a fridge, and temperature is 101, there's a serious problem here, right? Something's really wrong. But if the system is an oven and temperature is 101, then maybe that's not a problem at all. Maybe that's just normal. The temperature is warming up, right? It's warming up. It's got to get to 190. It's 101 at the moment, okay? And what if the system is a car engine? Well, because the water in the car engine is pressurized, it actually goes beyond 100 degrees. So that would be normal. That would be a normal temperature. Nothing to do here. That would be urgent problem. That would be carry on with the heater on, and that would be do nothing because that's normal. So you have to understand the context, and you cannot write code that's actually beyond the most basic thing without these ideas of context and understanding discrete versus continuous and so on. So this is why we do this lecture now, because it's a bit beyond your coursework, but it's definitely part of a master's in embedded to understand this. So it may be beyond your coursework, but it's not beyond the course. This is quite important stuff to understand. Where do we get context from? We get it from the external environment and from the system itself, right? So context can be the system itself. So as a person, how do you feel right now? Where is that information coming from? Well, part of it comes from your environment and part of it comes from you, right? How do you feel? Do you feel warm? Do you feel cold? Do you feel happy? Whatever. So it comes from two areas, and the same with a computer system. How does the system, what is the system, what is its context? Okay, so it's what is the thing I'm connected to? If I'm a controller of a house, is a house warm? Is a house cold? Whatever, and the system itself. So maybe things like what are the threshold values? What is the history? What is the trend we've devised? So the context comes from these from the system itself and the environment the system is in, right? And your role as a designer is to gather the information you need to make the decisions. So it's not just having more sensors. Sometimes it's simply things like calculating a trend with the sensor you've already got. You might only still have the same sensors, but you make it more intelligent by looking at the trends in the data rather than just the data. So it doesn't mean have loads more sensors to measure more stuff, although it can do that as well. Can be that, but it also can be make more use of the stuff you have measured, the stuff you are sensing. And it's the two things put together. And sometimes it's combinations. So sometimes it's rather than saying if the temperature is this and the light level is that, if the temperature sensor is this and there is movement in a certain area, so maybe using two different sensors like that, maybe it's a combination of the two. So if there is movement when the temperature is greater than 5, do something. If it is dark and the temperature is low, do something. And it depends again on the application, but maybe it's not just looking at each sensor separately. Maybe it's looking at sensors in combination, saying if this sensor says that at the same time that sensor says that, that means something. But individually, the sensors don't mean anything. Temperature on its own is nothing. You're only worried about the temperature if, for example, if we were controlling the temperature in each room because we're doing an environmentally friendly heating system, we only want the heating on when there's a person in the room, right? So if the temperature is low and there's no one in the room, there's no movement as seen for the last, say, 3 minutes, then turn the heating off. Even if the room is already cold, don't heat the room because there's no one in that room. So you can see that it's not, to be so-called smart doesn't mean loads and loads of maths, or it could do in some cases, but it doesn't have to. Sometimes it just means making the system respond in a kind of intelligent way. And I think of it more like the kind of intelligence of insects rather than of humans. It's worth remembering that thought. They kind of, if you look at a simple insect, it actually behaves far more intelligent than any program you'll probably ever write in your whole life. Think about that for a minute. Think about an ant trying to find food. And I mean this now because I've been spending my whole life trying to write programs that are intelligent. I reckon an ant trying to find food will behave more intelligent than most code I've ever written, possibly more than all code I've ever written, just that one ant, right? Because it has an intelligence that is it's evolved for a start, but something that's evolved means over many generations, it's had a chance to keep the good bits and throw away the bad bits. So although it's got a very small brain, it uses its intelligence and its sensing of the environment in a very clever way. And most of the ant's behavior is stemmed from its environment, not from itself. But as I said before, the smart behavior can come from itself or from the environment, the context. Now, with smart systems, we're not trying to mimic human intelligence. That's more like the AI. That's right at the high end of this spectrum. We're more trying to mimic perhaps the kind of intelligence you would expect to find in an insect. Simply, if that area is hot, don't go over there, stay over here, or things like that. But then combining that with other things. Okay, so come back to that example with temperature. So if we know the instantaneous temperature is 101 and we have a rising trend, just hang on a second. Matt? Sorry, just getting rid of some background noise. Hang on. Right, so if we have a rising temperature and an instantaneous value, so suppose we have 101 degrees is the instantaneous value, and but it's rising already at 10 degrees per minute, and we want to get to 190, then we don't need to do anything because we have this extra information. It's already going up. So whatever the system is at the moment, if the heater is already on, if the oven temperature is rising and we're controlling the oven, don't change anything because it's doing what it needs to do. If, however, the temperature is 101 and is stable, then we need to add more heat. We need to turn the element on or add more power or something, because just being 101 is not, we don't know enough. Basically, we don't know enough if it's just 101. We need more information. The context of being rising trend and how strong the trend is makes our program all of a sudden really smart with hardly any extra information. All right, we need to look at some things, some averages and so on, some different ways of generating these values of trend and so on. So obviously everyone will have heard of averages, but averages are calculated in so many different ways, and there's a whole world of statistics which I'm definitely not going to be covering in this lecture. You can obviously look up the different formulas for different types of ways of doing various statistical functions, but calculating when you take the numbers, add them up and divide by the number of numbers, that's called an arithmetic mean. We shouldn't use the word average because average can be done in so many different ways. We should be more precise about what type of average we're doing. So we've got mode, median, arithmetic mean, moving average, all kinds of things, exponential moving average. So many different ways of taking an average. So an arithmetic mean is probably the most basic way. Supposing you've got 3 values and you want to take an average, well, you add them up and you divide by 3, and that's your arithmetic mean. You could write that function very easy, and you could take 3 temperature values and have the average, and you could change it to do a mean of 5 numbers or any number you want. If you have an unknown, a varying number of samples, then you could write a function like this, calculate arithmetic mean n, where you pass an array of values in and a count value, and you know how many are in the array, and you basically add them up in a loop. You need a loop now because you don't know how many there are in advance, and you divide by the count, and it's the same answer. It's basically the average of all the values in the array. These are really simple things. These can just add the first little step towards making this smart behavior. And then obviously, if we're going to, let me just go back a slide. Sorry. Okay, so this is calculating the mean. So the next thing is so sometimes rather than looking at the instantaneous values in isolation or as a trend, you need to know what is the highest value. So you may be, for example, there's various situations where you don't know what the range of values a system, an environment might find. So supposing you have the home heating example again, let's try to keep to the same simple set of examples: home heating, oven heating, things like this. Let's go to the home heating, right? If the system's going to be smart over time, maybe we might even call it self-configuring now. If we start doing some of these things like this I'm going to show you now, you might even have a self-configuring system where, suppose you install this temperature controller in someone's house. The system, when it's installed, and even the owner of the house don't know what is the highest temperature this house has ever been and what is the lowest temperature, right? Maybe the system might want to keep track of the highest temperature that it's ever been. And what did the user do at that temperature? They probably turned the heating off. and what is the lowest temperature. And maybe because of the different insulation in the house and where the house is located, you don't know how hot this house gets, how cold this house gets, right? So you could keep track of the highest value seen. You don't need to store all the data. This is really important because in the embedded systems, especially in microcontrollers, we don't tend to have much memory, not like a microprocessor or where we've got a disk drive connected or something like this. Normally we'll have quite a limited memory. So we only want to have one variable called highest and another one called lowest, and maybe keep track. And then you can make more smart decisions. So rather than saying the temperature is 25, what does that mean? You might say the temperature is 25 and the highest we've ever seen is 27. Now that means something, that tells you more. That now you can say, okay, so this is quite hot then. 25 means quite hot, really, in this environment. Whereas if the lowest seen is 3 and the temperature is, say, 12, well, you're kind of, this is not cold in the context of this particular location. It's cold maybe for the user's perspective, but for this location, it's not particularly cold. And you might also then have a way of setting off an alarm if the temperature reach a new high or a new low. You might want to warn the user, because maybe if the highest value for the last 3 years has been 27 and now we have 28, maybe the user needs to know that, because that's quite different. It's never been this high, or this house has never been below 3 degrees and now it's -1. So the system can be smart with simple formulas if you think carefully about what to be looking for and how to add this value into your code. So to keep this, and this is really memory efficient, because it only stores essentially you need one long-term store and one temporary store variable. So literally 2 bytes is enough to operate this function, really, plus your actual current value. All you do is you keep a track of the previous highest, you compare with your new value, and you either update the previous highest to be the new one if it's higher than before, possibly set some flag. If it is a new high, you might want to set another flag as well, or something, and then you return that value back. So something as simple as this, as I say, can make a big difference on the value of the behavior that you get. But internally, you're not doing much more work. You don't need any more sensors or anything. But all of a sudden, your system is providing a whole much richer behavior. Okay, so in a continuous system, let's go back to that just 1 second. This is a formula that's useful in a continuous system, because the whole point is we can keep track of the highest value without storing the full history. And that's really important, because in a continuous system, the complete history would be the temperature maybe 100 times a second for the last 5 years. You can't store all that. And even if you store it, what are you going to do with it? You can't process it. You're going to search it. You're going to draw graphs of it. What are you going to do with it? And if you start trying to read all that history data, it will take you a long time to make one decision. So it's pointless trying to store it. But just keeping track of the highest value, the lowest value, the average value, and then using them, that's really powerful. But storing all that history is bad. So in continuous systems, one thing that you have to change in your thinking is that you only want to make instantaneous decisions, but you want historical data. You don't want to make decisions that you have to search all the data. So it's a continuous system, but you want an instantaneous decision. And the instantaneous decision is only made by, for example, if you know the historical highest value, you can make an instant decision. Is the current value higher than the highest? So you haven't got loads of processing to do to make that decision, but the decision is based on the history. So you're kind of optimizing what information you have without loads of extra work, storing it, processing it, taking up all your memory. Okay, so this is really, it seems almost trivial, so simple, but actually the value is very, very high. Now, let's have a look at some data series then, some number series, right? And in particular, the reason why we don't necessarily want to base our calculations on the full history of every single new number. So let's assume we have a sequence. You can read this yourself while I'm talking, okay? This just explains the problem of having to store all the data, etc. But if we actually look at an example, it makes it really clear. If you have a sequence of say 5, 6, 5, 6, so that's kind of the average is going to be 5.5, right? If it keeps going like that, the average arithmetic mean is 5.5, and maybe that is because the way we're sensing it, the actual value is in the middle here, but temperature is actually 5.5, but we're sensing it and we're just writing it down in our memory to be the nearest whole number. So sometimes we think it's 5, sometimes it's 6 degrees Celsius, but actually it's probably in between those two. And that's just because of the limitation of the way we're measuring the temperature, right? So it could be something simple like that. Or it could actually be like this because the heating is coming on and going off, or something like this. It could actually be purposely changing like this, or it could just be that the way we're measuring it, the actual values in between. We don't really care, right? It doesn't really matter. The temperature is oscillating gently between 5 and 6. Now, suppose a new value comes along of 9. All of a sudden we read it, it says 9, right? So the temperature, if we look at the average, clearly the current value should make the average change quite a lot. And if we've got 4 values plus 1 new one, so we've got 5 values now. If we add them all up and divide by 5, we find the new average is now, the mean average is 6.2. So that new value has had quite a big impact on the average. And that will cause quite a big change in behavior in the code. Whereas if we have a long sequence where we measured this for much, much longer, and then we have this new value, we see the new value won't have much effect on the mean, because now you've got to add up maybe, I don't know how many are here, maybe 20 values of 5.5 average, and then add 9 and then divide by 21. That's approximately how many are there. I haven't counted them, but and then you end up with only a small change. So the new value doesn't really influence the mean very much in this case, but it does here. Now, if you have to store the whole history, apart from the fact that the new values is kind of diluted, imagine this is stocks in the stock market, right? If you've got a history of the price being 5 and then 6 and 5 and 6 and 5 and 6 for like the last few weeks, and all of a sudden the price is 9, well, that might make you do something. Don't know what, depends what it is, but it might make you do something, right? But only if you're looking at the average, well, maybe you don't notice the difference so much, and maybe you notice it more here and less here because you've got all this data. But also, processing this data takes more time. So the more data you have now is actually a disadvantage because you've got to process it, you've got to store it. So in a continuous system, having a big history is a disadvantage, but inside that history is valuable information. So it's an advantage and a disadvantage, right? So how do we resolve that? Well, here's an example that is used in a lot of systems, a lot of control systems, and again, I mentioned stock markets, for example. There's an example where this is used a lot in those kind of situations where you have a long history of data, but the current value is more important than the data from last week or last month. But that data from last month is still useful, but today's data is much more important, right? So what you want to do is keep a track. Suppose the data is like 4, 3, 4, 5, going along like this. If we have a moving average of 5, MA5 would be a moving average of 5 samples. We take these 5 and we take the average and we write the moving average is 4.4. We can't do it here because we haven't got enough data. So we don't know the moving average here. Some systems would just leave it at 4 and then we would put 3.5, would start half doing it, but it's not, you can't rely on this value until you've had 5 samples. So it's best to actually say -1 or some special number that says you can't, this is meaningless until you've got enough data. And this also explains, by the way, why some systems have to so-called warm up. You think, how can a computer system have to warm up? Sometimes the system won't work immediately when you turn it on. It waits a little while before it does things. Sometimes it's nothing to do with actually warming up the circuit. It's warming up the data history, because you can't do anything until you've got some of these samples. And if you start running big computer simulations of things, then you'll find that they will require a certain amount of sample data before they can do any predictions. So that sometimes is why. Anyway, here with the moving average of these values is 5 values, and the average is 4.4. And then if we then take a moving average here, it's 4.6. Well, obviously it's slightly higher because we've lost the 4's dropped off, but we've got a 5 on there, so we can see it would be slightly higher. And then you see that we take the next one. Well, we've added a 4 and we've taken off a 3, so it would be slightly higher. So we can see this appears to be correct, and you can see the values that would follow. And this is what's called an MA5, and this would be an MA10. You take 10 values, and of course you can't do anything when you've only got 9 values, so you have to wait. So there's a slight lag in the system being able to work, but when it does work, it's more accurate. But notice the important thing here, that when we're looking at these values, we've forgotten about these values now because they're old, and we've only got to store. We only have to store these values, right, to do the calculation. So suppose when we get up here and we're doing this one and we've just got these, we haven't got to store all this anymore. This is all gone. We've forgotten about all that. So we haven't got to keep processing it. We haven't got to keep storing it and keep track of it and loops going round dealing with it all. We've just got these small number of values. So moving average is very powerful because it cuts down the amount of history we need, and it cuts down the amount of processing time, and it cuts down the amount of actual memory needed. All right, and it also gives us more emphasis on the recent history rather than the ancient history of the system, which is normally more useful, right? Okay, so there's all kinds of different things you can do. Now, my favorite type of averaging is the most complicated one, but it is the most powerful as well. This is called the exponential mean, and this is super duper, and this is more powerful in a large number of scenarios. And the nice thing about this is, to store the historical mean, I only need 2 values. The current value, well, sorry, I have 3 values. I need the current data, the exponential mean number, and a weight value, a weighting value. So I need 1 constant, which is the weight, and I need 1 historical value and the new value. That's all I need. So 3 numbers in memory to keep the exponential mean. And this mean takes the history back, infinitely back, as far as you want to go as well. It's very, very clever. So what we do here is this. We have a formula which says the current mean value is this alpha value times the new value plus 1 minus alpha times the previous value. And the previous mean was calculated using the same formula 1 step back. And that previous mean, so you see this is like, this is going back in time recursive, right? Because the previous mean used the same formula with the previous mean before that. And to get the previous mean before that, you did the same formula with the previous mean before that. So if you start at the beginning, the first value is the current mean. And then the second value, the current mean becomes previous, and you use this formula and you get the new current mean. So working forward. So when you are at a particular point in time, to work out the previous history, you'd have to go back in time with the reworking your way through this, but you wouldn't be able to actually, because you wouldn't have stored all the data. But the point is the value keeps up with the system. So the current mean is always a reflection of a combination of the new value and the old mean value, and that mean value is a combination of itself, of the new sample at that time and the previous value before that, and so it goes back in history. But the point is, we can tune this depending on alpha. So we can use a bigger alpha. It puts more emphasis on the most recent sample. So the mean will respond more quickly to the current data. But some systems, we want it to respond gradually. We don't want it to respond too quickly when things change. We want it to gradually follow the trend rather than jumping up and down all the time. So we can make this less reactive by using a smaller alpha, and then that puts a bigger weighting on the history and less on the current. So we can tune this to see how much weight is on the current, how much this system reacts to the current value against how much this system values the history. And you can tune it. And the end result is you only have to store the current mean and the alpha, and the only other data you need is the new value. 3 things. And then you generate the current mean becomes the previous mean, and you use this formula with the new value, and then you regenerate the new current mean, which you store in the same place that the other current mean was in. So you need one extra storage place as a temporary, because you have to copy this into that, okay, then use calculation and then write over this, right? It's a very simple formula. It's 1 line of C code, or any language actually. It's 1 line of code. Now, choosing alpha is complex. You need to do experiments to get your system accurate. And normally I've found that you never need an alpha smaller than 0.05, and it's kind of dangerous almost to go beyond about 0.25. But you can do what you want. You can try anything, but normally it's in that range. Okay, so you take the new value to influence the mean, but you don't want just the new value. You don't want to completely throw away your history. Okay, now here's a formula. Here's an example of how to calculate it. The important thing to realize is you need some kind of checking to make sure that alpha is between 0 and 1. If alpha is outside the range 0 and 1, then you can't use this formula. So you need to return all your code, by the way. This is something else in your coursework. None of you did any of this because you weren't asked to, and I don't think you've been trained to do it. But in all code writing, the first thing in any function you do is check the parameters make sense before you do anything. So you always should do safety checks. You know, the new value is this. Is that a legal value? If you're if you're looking at samples coming in and something is wrong in your code and you've got a value that's out of any kind of meaningful range, you don't just carry on. You should flag up that's not possible. It's something wrong. And then you obviously it's a form of dynamic, it's runtime error checking. So if the alpha value is wrong, is meaningless, then that is reported. Only if the alpha is legal, then you can calculate. And you say, okay, the new mean is the new sample times alpha plus the current mean times 1 minus alpha. So if it's 0.2, and that's 0.8. If it's 0.1, that's 0.9. So the total is times 1 altogether. It's a combination of the sample and the history times, you can never have more than or less than 1 in total, because otherwise your value will just increase or just decrease continuously. It's got to generate an average that's stable. So this, whatever this is multiplied by, this must be multiplied by 1 minus that. So the total factor is 1. You take a bit of that and a bit of that, but the total weight must always be 1. Okay, here's an example of what I'm trying to say with a graph that maybe make some of this clearer. So if we have the data, which could be, let's go back to, say, the temperature in the room. It's a bit extreme. Maybe it's okay because look, it goes up to 26 there, it goes over 40. This is probably okay for room temperature. Could be anything though. This on this graph, I'm not saying this is room temperature. It could be, I don't know, it could be stock price. It could be a noise level on a microphone or something, right? But let's assume it's room temperature because it seems to be in a good range, okay? and you see the raw data's quite changes quite a lot. Maybe if it was a room, this could be heater coming on and off. It could be someone opening and closing the door. It could be maybe people are in the room moving around, creating heat. Maybe it's a kitchen where the oven is on and it's very hot. All kinds of things could be causing the change. It doesn't matter really what is causing the change. The fact is, this is the data and it's changing quite a lot. And it's got a certain range. It kind of doesn't go below about 15. It doesn't go above about 25, okay? Supposing we want to have an average of this. Well, if we start with the arithmetic mean and we store all values to date, so we have like a 100% history, all the values are stored, okay, and this problem of the new value has less effect. So if we take all the values to date and we take the mean, then we find that initially, as we get changes, this dotted line follows the changes. It's not bad, is it? This dotted line kind of represents what's going on there quite nicely as a single number representation. But over time, because the average of this will just come down to mid-range, about 20, right? The average of this will eventually stabilize at 20. If you've got thousands of samples around about 20 average, then the new value has hardly any effect. And you see this dip here hardly has any effect on the average, and this spike here has hardly any effect. So the mean, when it's over a long period, doesn't really help us at all. It just says the long-term average of this system is about 20. Yeah, well, we can see that. The long-term average is about 20, but what use is that if we're making decisions right now? We want a bit more recent. What's the average in the last hour? How do we get that? So then we start thinking about some of these other techniques. And I haven't put all the moving average ones on here. I maybe should have put them on as well. But here we've got the exponential means with different alpha values. And you can see that a low alpha, such as 0.05, this grey line, which is here, this is quite nice actually for a smooth system. It's not very responsive, but you get a nice control from that. You don't get things suddenly getting turned on, turned off, like the heating's turned on, the heating's turned off, heating's turned on again, the heating's turned off. You get a much smoother response, but it's not very quick to react. So that's a plus and a negative from that. And then if you have a much higher alpha, and this is your raw data, you'll find it responds much closer to your raw data. But again, it's much more meaningful than the arithmetic mean after time, and it cuts off the extremes of your data. So your data's quite extremes, but the exponential mean is cutting off those extremes. Okay, it's reducing the spikes, but it's still reacting quite strong. So here, obviously, the exponential mean reflects that the temperature went quite cold, but it doesn't have every little up and down of the data. And the same here, the exponential mean reflects that the temperature got quite hot, but doesn't have all the ups and downs. So your heater's not going on, off, on, off, on, off, and that kind of thing. You get a much smoother control, but you don't get that high sort of reaction speed. It's 10 o'clock, so because this lecture we can stop on any slide really. Shall we have a break now and start again? Because you're all at home, you don't need such a long break, I guess. Just go make a cup of tea, something. So yeah. Shall we take? Is 15 minutes okay?
Yeah.
15-minute break. I'll see you at 10:15. I'll leave the Zoom on and everything. I'll see you in 15 minutes.
Sure.
What? Oh, yeah. Okay.